Welcome to this explainer. When we look at modern AI today, when we watch a large language model effortlessly generate a perfectly reasoned essay in a matter of seconds, it honestly feels like magic. It feels like this incredible technology just dropped out of the sky a few years ago. But the truth is actually far more cinematic. ChatGPT didn't just appear overnight. It stands on over a century of mathematical ideas. So today we're going to uncover a lost piece of technological history and discover the forgotten ancestor of modern AI.
Okay, let's dive right into this mystery. We're going to jump way back in time, long before ChatGPT or any modern algorithms existed, and ask a really fundamental question. How did early computing actually tackle language? Seriously, if you don't have billions of parameters or sophisticated neural networks, how on earth do you teach a machine to write?
Picture the computing landscape of the 1950s for a second. We're talking about massive, room-sized machines. There are absolutely no GPUs, no neural networks, and there are definitely no transformers. The hardware is just incredibly bare bones, and the whole concept of a machine somehow understanding text was practically science fiction. And yet, the very seeds of artificial intelligence were already being planted.
Chapter 1. Before ChatGPT. So long before deep learning came into the picture, the secret to artificial intelligence wasn't about teaching a machine logic or reasoning or even grammar. Nope. It was actually rooted in something much more primal, pure probability. Early text generation wasn't about understanding meaning at all. It was quite literally just about calculating the mathematical odds of what comes next. Think about it. If you have the word pizza, what is the exact mathematical probability that the very next word is margarita? Well, that beautifully simple question is the absolute bedrock of everything that follows.
Chapter 2. The Chain. To really wrap our heads around this, we actually need to leave the modern era completely behind and travel all the way back to 1906 to Tsarist Russia. Because right here, a frankly petty mathematical feud over theology accidentally birthed the foundation of modern AI. On one side, we have Pavel Nekrasov, a devout thinker who strongly argued that independent human decisions proved human free will. And against him, we have Andrey Markov, an atheist mathematician with absolutely zero patience for nonsense, which actually earned him the fantastic nickname Andrey the Furious. Markov just wanted to prove Nekrasov entirely wrong. He believed that events could absolutely be dependent on each other, connected in a chain, and still result in stable statistical averages.
And to prove his rival wrong, Markov formalized what we now call the Markov property. Let this sink in for a second. The future depends only on the present, not on the sequence of events that preceded it. In math, this is known as the memoryless property. It's kind of like, imagine you're standing at a crossroads. In Markov's system, the algorithm only looks at the exact state it is currently in to decide its very next move. It completely ignores how you actually got to that crossroad in the first place. It has zero memory of the past, just the current state.
Now, this simple, memoryless math turned out to be a massive game changer, because you could suddenly ignore the incredibly complex history of a system and just look at its present state. The math became highly computable, and it went on to predict almost anything. It was used by Stanislav Ulam and John von Neumann to literally model neutron fission for the atomic bomb using Monte Carlo methods. It's used to forecast whether it'll be rainy or sunny tomorrow. It even became the foundational math for Google's original PageRank algorithm, navigating the entire internet. But the crazy thing? Markov didn't care about any of that. He literally just wanted to win a theological argument about text.
Chapter 3. Teaching AI language. So how exactly did Markov actually prove his theory? Well, he needed a system of dependent events. He decided to take Alexander Pushkin's famous Russian poem, Eugene Onegin, and he completely stripped out all the spaces and punctuation, turning the whole thing into just one massive continuous string of text. And then he sat down and hand-counted 20,000 letters, just by himself. Through this, he found his baseline distribution. In this specific text, 43% of the letters were vowels and 57% were consonants.
Armed with that data, he basically built a prediction machine. Markov meticulously counted how often a vowel followed a vowel, or a consonant followed a consonant, proving that a letter is highly dependent on the one right before it. For example, if you're currently on a consonant, there is a massive 67% chance the very next letter is going to be a vowel. He essentially built a transition matrix. He could start at literally any letter, roll the dice based on these exact percentages, and generate a totally new sequence. And guess what? After thousands of steps, the random generated sequence stabilized right back at that exact 43% to 57% ratio.
He had definitively proven his point,
A dependent system still converges on stable averages. He ended his paper with this epic, incredibly spiteful mic drop moment aimed right at his rival, saying, "Thus, free will is not necessary to do probability." I love that. He had no idea at the time, but Andrey the Furious had literally just invented the probabilistic language model.
Now let's fast forward a bit to the 1940s. The legendary Claude Shannon took Markov's exact logic, but instead of applying it to single letters, he used whole words. It worked like this. Step 1, observe the current word. Step 2, calculate the transition probabilities of what word usually comes next. And step 3, generate the most likely next word. Suddenly, computers could generate flowing sentences one state at a time. And honestly, some of these sentences were surprisingly believable. But others, well, they were hilariously wrong.
Chapter 4. The memory problem. You see, this early technology faced one major hurdle, a truly fundamental flaw when it came to generating human language. Think about a sentence like this. The cat that chased the mouse ran into the house because. Now, if you ask a simple Markov model to finish that sentence, it hits a massive roadblock. Because of that memoryless property we talked about, by the time the algorithm reaches the word because, it has completely forgotten about the cat and the mouse from the beginning of the sentence. It literally only knows the current word. So, while Markov's memoryless property made the math highly efficient and computable for the time, it produced absolute context-free gibberish when it tried to write long paragraphs. A Markov chain forgets immediately. Contrast that with the modern transformers we use today. They use a revolutionary attention mechanism to literally look back at every single previous token in the sequence, which allows them to maintain perfect context from start to finish.
Because of this flaw, decades of computer science basically became a desperate race to overcome this exact memory limitation. Researchers tried using things called n-grams, which widened that context window just a little bit. Then came neural networks in the 2010s, things like RNNs and LSTMs, which tried their hardest to force the algorithm to remember a longer sequence of words. Literally everybody in the field was just trying to fix Markov's memory problem.
Chapter 5. From Chains to ChatGPT.
Okay, let's resolve this mystery and finally connect this 120-year-old math directly to the technology that's changing our world right now. Just think about this evolutionary journey. We literally climbed from a bitter Russian poetry feud in 1906 straight through the statistical models of the 90s into the deep learning boom of the 2010s, all the way up to 2017, when the famous Attention is All You Need paper officially birthed modern transformers. It is all connected.
And what that timeline shows us is honestly profound. The biggest breakthrough in the history of artificial intelligence wasn't about teaching AI more words. It was about teaching AI to remember. The invention of attention, finally, beautifully solved the memory problem. It allowed the AI to look at the entire context of a prompt all at once, while still doing exactly what Markov designed it to do over a century ago, simply predict the next token.
So what does this hidden history actually mean for us today? Well, 3 things. First, Markov chains introduced the very concept of probabilistic language modeling. Second, it was the memory limitations of those exact chains that drove decades of relentless AI innovation. And third, even the most insanely advanced multi-billion parameter AI that you're using on your phone right now, it is still, at its core, essentially answering Markov's original question. Based on the current state, what comes next?
When you strip away all the massive neural networks and the complex prompt engineering, the very heartbeat of AI is still just a game of probabilities. I'll leave you with this final thought as we wrap up this explainer. The road to artificial intelligence didn't begin with transformers. It began with a chain.